Okay, I was absolutely blown away when I dug into the research for today's explainer, and we are going to explore this whole concept together. Seriously, it completely changes the way we think about those invisible signals constantly floating through our homes and offices. It actually has this incredible sci-fi feeling, like the internet routers we already have sitting on our desks are secretly capable of watching us. So today we're looking at a fascinating emerging technology called Wi-Fi sensing, and we'll be exploring how we can leverage everyday Wi-Fi signals for cutting-edge presence and movement detection. Let me ask you something. Can your Wi-Fi detect your heartbeat? It sounds literally like science fiction, right? But the answer, incredibly, is yes. And the most mind-blowing part about this whole thing is that it can be done without the need for any cameras, without strapping on any wearable sensors, and without any expensive specialized medical equipment whatsoever. You can do it just using the radio waves that already power your internet connection. Okay, let's dive into this. Here is our roadmap for the explainer today. We'll start with seeing without cameras, dive into the science of Wi-Fi, explain why smartphones fall short, get hands-on building with the ESP32, and wrap the whole thing up with ethics and future upgrades. All right, Section 1, Seeing Without Cameras. Let's cover the basics. So Wi-Fi signals, just like any radio waves, are constantly interacting with the physical objects in their environment. Think of it like walking through a room filled with invisible spider webs. Every single step you take subtly tugs on those threads. The signals bounce, they scatter, they pass right through certain materials. When a living being moves within the path of a Wi-Fi signal, it causes these very, very subtle changes in the signal's properties. So instead of using a camera lens to see a person enter a room, we can just analyze the disruptions in the radio waves filling that room to infer incredible amounts of information about presence, movement, and yes, even vital signs. Moving right along to Section 2, the science of Wi-Fi, specifically RSSI versus CSI. There are basically two primary metrics we need to talk about here. First up is RSSI, or Received Signal Strength Indicator. Now, this is essentially just a measure of the power level of a received radio signal. If you physically walk between a Wi-Fi router and your mobile phone, the RSSI drops because, well, you've obstructed the signal. It's simple enough, but it's a relatively coarse metric, and it is highly susceptible to environmental noise. But the real magic lies in CSI, or Channel State Information. While RSSI is just a broad, overarching measure, CSI captures highly detailed information about how the signal actually moves. It captures changes across different signal frequencies, which we call subcarriers. You can think of subcarriers kind of like multiple lanes on a massive highway. Instead of just knowing if there's a general traffic jam somewhere on the road, CSI tells you exactly what's happening in every single lane simultaneously. Channel state information really is the secret sauce here. Because it captures all those fine-grained details across multiple subcarriers, it is significantly more sensitive to subtle environmental changes. We aren't just talking about sensing if someone walked through a heavy wooden door. We are talking about sensitivity levels high enough to detect the tiny, minute chest movements of a person breathing, or even the rhythmic beating of a human heart. It's absolutely wild, and it is the true foundation for advanced sensing applications because it offers vastly higher accuracy than RSSI ever could. Now, what's really interesting about this next slide is, well, Section 3, Why Smartphones Fall Short. You're probably thinking, can I just use the phone in my pocket for this? Well, if you tried to build a CSI-based detection project using an off-the-shelf smartphone, you would hit a brick wall. Most commercial mobile devices simply do not provide direct access to raw CSI data through their standard Android or iOS APIs. And these restrictions exist for really good reasons, mostly security, privacy, and hardware abstraction layers. To get to the CSI, you generally need root access or entirely custom firmware. Without that, you're stuck with that coarse, noisy RSI data we just talked about, which is totally prone to false positives. When you see smart devices like the Google Nest Hub offering advanced presence or sleep sensing, they aren't using standard mobile phone architectures at all. They actually rely on dedicated hardware and specialized algorithms integrated at a much, much deeper level. Which perfectly tees up Section 4, Building with the ESP32. Let's talk about a practical approach. So if you're looking to actually build this yourself, say for a really cool science exhibition, a much more practical approach is using dedicated low-cost microcontrollers like the ESP32. To get started, you literally just need a few things. You'll need 2 ESP32 development boards, some USB cables for power and programming, a computer to write your code, and maybe a breadboard if you want to get fancy with it. The absolute magic of the ESP32 is that it has integrated Wi-Fi and Bluetooth. And, crucially, this is the big one, it allows direct access to that highly detailed CSI data we need. In honesty, the software setup, it's surprisingly straightforward. You basically just start by installing the standard Arduino IDE on your computer. You add in the ESP32 board support, and then you just grab a suitable ESP CSI library from GitHub. There are some truly amazing open source tools readily available right now, like the Espressif/ESP CSI repository. These tools are exactly what empower you to unlock that raw, unfiltered signal data. Okay, let's look at the actual system architecture and see how this becomes a functional sensor. A typical setup requires two boards working together in tandem. The first one is your sender board. Your goal here is to write a simple Arduino sketch configuring this ESP32 to act as a Wi-Fi access point. Its one and only job is to send out periodic, continuous Wi-Fi packets. Consistency is absolutely crucial here. You need a rock-steady baseline of packets so that any changes in the physical environment between the two boards can be reliably detected. Think of this sender board like a metronome, constantly ticking out a perfect, steady beat so that the receiver can notice even the slightest disruption in that rhythm. Next up, we have the second half of the equation, the receiver board. Now, this board has a much more complex job. It acts as the listener. Your code tells it to initialize the Wi-Fi interface specifically to capture that raw CSI data, and it processes the incoming frames to extract all those microscopic changes in amplitude and phase for every single subcarrier of the signal. But here's the catch. Once you capture that data, it is incredibly noisy. You can't just take the raw data and expect it to work. You have to apply filters to smooth it out, average the signals, and you might even need to run algorithms like principal component analysis, or PCA. PCA is essentially this brilliant math trick used to separate the important human movements from random, meaningless background noise. Plus, you have to strictly calibrate your system by collecting a baseline of CSI data when there is absolutely zero movement present in the room. This essentially tells your algorithm what an empty room looks like, so it can properly set the thresholds for actually detecting someone. Finally, Section 5, Ethics and Future Upgrades, taking it beyond the basics. Once you have a basic system running, the potential upgrades are literally staggering. I'm talking about integrating machine learning algorithms like support vector machines or full-blown neural networks. By feeding your process CSI data into a machine learning model, you upgrade the entire system so it doesn't just know if someone is in the room. It can actually classify different types of movement or, get this, even identify specific individuals based entirely on their unique, invisible movement patterns disturbing the Wi-Fi field. No way, right? And this leads to some downright incredible real-world applications. If you're building this for a science exhibition, think about framing your project around these use cases. Fall detection for the elderly that preserves their privacy, highly accurate sleep monitoring without having to wear a bulky smartwatch to bed, stealthy intruder alerts, or intelligent smart home occupancy sensing that actually turns off the lights when a room is genuinely empty. You could even set up multiple sender and receiver pairs to triangulate exactly where a moving object is in a massive space. It's a real game changer. To kind of sum up the technical side of things, there's a fantastic quote from the source material that really stuck with me. Leveraging dedicated microcontrollers like the ESP32 offers a highly feasible and educational path for a science exhibition project. By stepping away from those restrictive mobile phone APIs and utilizing the ESP32 instead, you unlock the hidden, raw power of Wi-Fi signals. You get to create an innovative project that proves Wi-Fi is so much more than just a way to browse the internet. It's actually an omnipresent sensory network. But before we officially wrap up, I want to leave you with one final vital thought. Wi-Fi sensing is incredibly powerful, yes, but as this technology scales, it brings up some massive ethical considerations. In a future where literally every Wi-Fi router is a potential motion sensor, how will we protect our privacy? Now, if you are building this for an exhibition, you definitely need to clearly state that your system doesn't store personal data. But on a broader societal level, as this tech moves into our daily lives, balancing the amazing benefits of invisible health and safety monitoring against our fundamental right to privacy is going to be the next great challenge. Thank you so much for joining me for this explainer today. I really hope you found this as fascinating as I do. Keep learning, and I'll catch you on the next one.